In this video, we're going to review how to use L'Hopital's rule for evaluating limits of functions. First, as a reminder, here's L'Hopital's rule. L'Hopital's rule applies when we're looking at the limit of a quotient of f over g and we get the indeterminate form 0 over 0. And the rule says our original limit will equal the limit of f prime of x over g prime of x still as x goes to a, assuming this new limit exists or is infinite. You can think that having some information about the rates at which the functions approach 0, i.e. by their derivatives, gives us some more information. Note, if needed, we can also apply L'Hopital's rule repeatedly. L'Hopital's rule also applies for the indeterminate form infinity over infinity in the same way. In this case, both numerator and denominator must be infinite for the rule to apply. So L'Hopital's rule is helpful when we can't easily use algebra to try to manipulate the limit involving in an indeterminate form. Before we do a few examples, however, here is a reminder about indeterminate forms for limits. We have two basic indeterminate forms, 0 over 0 or infinity over infinity, and a limit must be one of these forms for us to apply L'Hopital's rule. There are other indeterminate forms, however. Some powers are indeterminate. 1 to the infinity, 0 to the 0, and infinity to the 0 are all indeterminate forms. Also, infinity minus infinity is indeterminate, and infinity times 0 is indeterminate. Anytime we have one of these indeterminate forms, typically we'll need to manipulate our limit algebraically to get to the indeterminate form 0 over 0 or infinity over infinity, so we can apply L'Hopital's rule. For comparison, there are many forms for limits that are not indeterminate. For example, infinity times infinity will approach infinity. You can think big times big is big. Or 0 divided by infinity is 0. You can think small divided by something big is small. In these cases, L'Hopital's rule does not apply, and we don't need it to evaluate the limit. Next, we're going to look at two examples. Notice if we try to evaluate the limit directly, we get e to the 0 minus 0 plus 1, or 0 in the numerator, and 5 times 0 squared, or 0 in the denominator. Thus we have the indeterminate form 0 over 0, and we can apply L'Hopital's rule. By applying the rule, we have the limit as x goes to 0 of 2 times e to the 2x minus 2, differentiating the numerator, over 10x by differentiating the denominator. Notice I've written the letters LHR over the equal sign to indicate we've used L'Hopital's rule. Again, by evaluating directly, we get 2 times e to the 0 minus 2, or 0 in the numerator, and 10 times 0, or 0 in the denominator. Again, we have the indeterminate form 0 over 0, and we can apply L'Hopital's rule. Now we have the limit as x goes to 0 of 4 times e to the 2x over 10 by differentiating top and bottom, and by evaluating directly, we get 4e to the 0 over 10, which is the same as 4 over 10 and not indeterminate, or by simplifying, we see our limit is 2/5. Notice here the indeterminate form 0 over 0 yielded 2 over 5 as the final answer. And we needed to apply L'Hopital's rule or do some other work in between to determine our limit answer. So now let's take a look at example 2, which has the form of a power, which I think are some of the trickiest indeterminate forms to recognize. And by trying to evaluate directly, notice we get infinity to the 0, as our exponent is approaching 1 over infinity, or 0. This is an indeterminate form, and you can think that we have a base that is growing and an exponent that is shrinking, and those two things are in conflict with one another. Without more information, we cannot tell what happens. So we need a way to turn this into one of our basic indeterminate forms, either 0 over 0 or infinity over infinity. And the secret will be to use the natural log function. I'll start by labeling my original limit L. And then I can take the natural log of both sides to get the natural log of L equals the limit as x goes to infinity of ln of x to the 1 over x. This is helpful because now we can use properties of logarithms. In other words, my limit is the same as the limit as x goes to infinity of 1 over x times the natural log of x. Notice we've used the power property for logarithms. That is, natural log of x to the r is the same as r times natural log of x. I can rewrite my limit, and now it clearly gives us an indeterminate form of infinity over infinity. As x goes to infinity, so does natural log of x, and so does x. Note, we can use this as confirmation that our original form, infinity to the 0, should also be indeterminate, as all we've done is move from one to the other by some form of algebraic manipulation. So by applying L'Hopital's rule, we get the limit as x goes to infinity of 1 over x over 1. Note, I've differentiated the top and bottom again. I can rewrite my limit, and now evaluating my limit, the limit as x goes to infinity of 1 over x is just 0. I have to be careful, however, to remember we started by taking the natural log of both sides. So what we really have found is the natural log of L. And we know that that's 0. So solving, e to the 0 equals L, or L equals 1. Since L was our original limit, we can conclude that the limit as x goes to infinity of x to the 1 over x must be 1. Notice that in this case, our indeterminate form infinity to the 0 yielded 1 as the final answer. And we needed to do that work in between to figure it out. And that concludes our video.